My name is Jadea Hudson, and welcome to Physics 2211 Lab 5. Now, I'll be focusing on the falling slinky. In this experiment, I'll be observing, then modeling the motion of a slinky in free fall, assuming the slinky is held from the top end before being dropped. That's very important to how this experiment will be played out. Now, I'll be predicting its behavior immediately after the drop. And I predict that the bottom will move upward slowly and that the top will move at a faster pace downward until they are finally moving together as one. And here is what actually happens.
But this is going to be really tough to see. So how are we going to actually determine what the bottom end stayed completely stationary even after you let go at the top? It waited until the whole slinky had collapsed down to the bottom before it itself.
And as you can see, I was wrong. Continuing. Now, the purpose. I will analyze, using Tracker, the motion of a slinky in free fall, then comparing the information that I acquired from this to a computational model using closed grip of a slinky falling. And we're going to be using some of the fundamental physics principles. Now, we'll be using Newton's second law, momentum principle, given here, the velocity update formula, given here, and the position update formula, given here. Now, the components that this experiment will be using, of course, we'll be using change in energy of our system, and here's what the equation is right now. And we also have a free body diagram to demonstrate the forces acting upon our slinky, with our slinky being the center of mass right here, and we have the drag force, and we have the force of the slinky, and then we have the force of gravity. And when something's falling, of course, there'll be like air pushing up on it, and the force of the slinky would also be pulling up at the same time you would be thinking down. But we'll get into that later. We will look at this problem in relation to the spring's center of mass. We have the free body diagram shown with three forces to consider, which are what I just talked about, but just making sure you know what I was talking about. Now, the video tracking. We have our initial conditions as the mass being 1 kilogram, the height of the man being 1.75 meters, and the frames per second being equal to 10.5. The Y position is what the point of focus was, and I also set the origin of my axis centered at the spring's initial bottom height. Now, in the computational model, first we have our initial conditions. So, I used the same values from my experimental procedures as well, and additionally defining the acceleration due to gravity as 9.8 meters a second per second. I also defined the proportionality constant for the drag force as well as the initial position based on the value in Tracker. Computational model, forces in motion implementation, my apologies. Now, we have the use of the force equation here, and with updating motion, we use the velocity and position time step equations to increment the position and velocity of the slinky at each time step. We then increment the time at the end of each loop. We also use, my apologies, use of force equations. We have F net equals weight plus F tension. In this case, the tension force is in the same direction as gravity. Cool, so we don't have to do anything extra. Also, updating motion. We use the velocity and position time step equation to increment the position and velocity of the slinky at each time step. We then increment the time at the end of each loop. Now, from this, we find in both the computational models on the left and the observational tracking on the right, which in other sense is just Tracker, the end of the spring was stationary until the top of the spring fell and the spring got to its relaxed compressed length, after which the whole spring fell together. Now, discrepancies in the data are one part that I like to bring up. Small mistakes in observational analysis data could result in human error when clicking through the frames to track the bottom of the spring. Additionally, the times for the two loops in the simulation could be incorrect as they were manually chosen based on observational analysis. And here is the other part of the discussion. We found that when a slinky is dropped from the top and is in free fall, the bottom of the slinky remains stationary until the top of the slinky reaches the bottom, after which the whole spring moves together to the ground. This makes sense since the center of mass is not at the bottom of the spring, and because the spring is initially hanging from hand. When the spring is dropped, there should be no immediate effect on the bottom of the spring, since only the top is dropped and the bottom is already hanging. Thank you.